Okay, so yesterday we did this axiomatic approach to sets, to algebraic objects. So this a set F will be called a field if it has two operations, which we will continue to use plus and multiplication, addition and multiplication, where addition behaves following the first axiom. So there A plus B has to be an associated element in the set. By additive identity, what I meant was that A plus 0 should be A. Okay, this is the meaning of additive identity, in case it was not clear. And relative to this identity, there is an inverse. So for A, there is a minus A, which means A plus minus A is 0. And similar thing for product, where multiplicative identity means A multiplied by 1 is A, and relative to this, there is an inverse, which means A times A inverse is 1. Distributivity was clear and commutativity was implicit. We assume operations to be commutative in a field. And associativity is basically that brackets aren't required. So A plus B plus C, you can do parenthesization as you want, answer doesn't change. Same with A times B times C. Okay, it's free of parentheses, except for distribution, you have to draw parentheses, of course. And then we saw many examples. Any questions? So famous example, natural examples are obviously rationals, reals, complex, and other famous examples are these prime fields. Composites don't give you field. Then we have this cancellation result. If something times something is 0, then one of these things has to be 0. Or contrapositively, if you multiply two non-zero things, you can't get 0. And here we also prove this result, that what is A multiplied by 0, right? So this is, it needed a proof that it's 0 because although it is written 0, but it may not behave as the normal 0, right? It's just additive identity. So how does it behave with multiplication? That needs to be worked out. But fortunately for you, here A times 0 is 0. It cannot be anything else. That's the proof. So 0 behaves like 0. Sometimes it may not behave as 0. For example, we constructed this field which is where 0 behaves as 1, right? But if that happens, then everything is 0 or everything is 1, whatever is your religion. And then we define characteristic, which is how many times should you add 1 so that you get 0. If that doesn't exist, then we call that to be 0, which is the case in usual fields, but for prime fields, it's a number which is a prime number, the same as this modulus p. We showed that for finite field, it's always prime, and for infinite fields, it may be either a prime or it may be 0. Okay, those are the characterization results. Any questions till now? So by prime field or Galois field, we will mean this FP field. That's the most important field in computer science. Other fields are not so often used. This is the most popular one, especially, I mean, even F2 is important. So when P is equal to 2, what is F2? F2 is basically you have just 0, 1, or I should say maybe Z slash 2. So you have just 0, 1 and the addition multiplication is mod 2. So it's fairly obvious what happens. So 0 plus 0 is 0, 0. Plus 1 or 1 plus 0 is the same thing, 1, and 1 plus 1 is 0. Right? So this is important that 1 plus 1 is 0. It's not like OR. It's very different. There is a term for this in computer science. What is this operator? It's the exclusive OR. So it's so important here that there is a name for this. So this XOR that you have learned, it's basically the finite field F2. And for multiplication, you have anything you put, you will get 0. And similarly, anything times 0 will also be 0. So all that remains is 1 times 1, which will be 1. So this multiplication is what in computer science? This is the AND, right? So you take AND and XOR and you have the first finite field. Okay, that is what you are used to. But we will not stop at that. We will take it to a crazy level of generality. But to start doing that, we will have to now look at we have to go beyond numbers. So what we will do is we will look at functions over numbers. And this will also be an attempt to answer the question that are there other finite fields of characteristic P? Right, so you have seen a unique one, Fp, but are there other finite fields? So also for that purpose, we will go to functions over numbers or over fields. And in computer science, the only function which is important is polynomial. So specific, in particular, we will study polynomials. So over a field F, a polynomial is what? I don't think we have studied it in this course, but obviously it keeps appearing. Like for a matrix characteristic polynomial, you know what it is. You introduce a new variable x. So that is a polynomial. So let's embark on that study. So polynomial is just use a new variable. Right, so this x, so for example, I mean if you take the example fx equal to x square plus 2x minus 1. So when you write this integral polynomial, so 1, 2, minus 1 are the coefficients, x square, x, and 1 are the monomials. And here when we write x, we don't think of it as a number or anything. Right? This is a, as you know, it's a letter, it's an alpha in the alphabet. So it's not supposed to be a number, it's supposed to be what is called a formal variable. And the only physical interpretation of this is that it can take all values. So you can evaluate x at 0, 1, or integers, or rationals, or reals, or complex, and beyond. Right? So it takes all possible values. So which is the same concept as a variable in a programming language like C. It is exactly the same. There is also an associated type. When I say field f, then clearly x can only take values which are related to f. It cannot take values completely different from f. Yeah, so that's the polynomial you are used to. And we can also use many variables. Then you get multivariate polynomials. So you can use x1, x2, xn, finitely many variables, which is what happens in a C program. They may have, I mean, in this case, they will all have the same type, which is the type of the field f. But in general, in C program, they may have different types. Okay, so those are the two keywords. So a polynomial has coefficients and monomials and terms. Right, these are the keywords we'll use. Coefficient will just mean the constant that appear inside it, like this 2 and -1. And monomial will be this a variable power which appears, like x square and x to the 0. Or it can be x1 times x2, x1 squared times x2, and so on. Can it be x1 by x2? So we don't allow that, right? You are only allowed to multiply and add. Addition, multiplication are the only operators. You don't divide by variables. And term is any summand. So 2x is a term, -1 is a term, x square is a term, and so on. If you have 3x squared, then this 3x square is a term. So definition of monomial is basically product of variables. And so what is the set of polynomials called? Where do polynomials live? The set of polynomials in the variable x over field f is called, so that's the standard notation. F square bracket x is the set of all polynomials in one variable. It's called the polynomial ring. Right, so it's basically the set of nicest looking functions over the field. The field, you can think of it as the field of rationals, or you can also simply take a ring like which is the ring of integers. Then you are looking at all the integral polynomials in one variable. So examples are, well, let's not take zx, let's just take field. So qx, rx, complex, fpx, and so on. right? So these are the polynomial rings in one variable, univariate polynomial rings. Now in the ring QX, do you have this element? So if you do an infinite sum on the terms, is this an element of QX? It's a trick question. In JE, you are taught how to sum this, right? You get 1 over 1 minus x. But do those things make sense in QX? So there is no axiomatic basis for that. Right? We have not given any axiom which can allow you to do that. So it is best not to do that. So this doesn't exist. So how does then in JE you are taught that this has this sum and you can approximate and all that. So to do all that you have to do more courses. We'll not discuss it here. But in the polynomial ring you are only allowed finite additions. Okay, you cannot take infinite sum, you cannot talk about convergence, divergence of a series and those things. That's those axioms we have not given you. And so what you can do is you can add two polynomials and you can multiply them. That is given in the axioms. So so for all A and B in the polynomial ring, A plus B is also in the polynomial ring. Right, that is the same as you were taught in school. You basically, okay, this needs more writing. So A, if you think of A as A0 plus A1x, A2x square, and B as B0 plus B1x plus B2x square and maybe B3x cube, where AIs and BIs are field elements. They are constants. You can think of them as just numbers 1, 2, 3, or minus 1, minus 2, minus 3. Or you can also use 1 by 2, 1 by 3 if you are in rationals. Then the sum of this is, what will be the first term when you add up? It will be A0 plus B0, right? Second term will be A1 plus B1 times x, and so on. Last term will be, the leading term it is called, will be B3x cube. Okay, so the natural thing will give you addition, and similarly you can multiply. How do you do multiplication here? In the case of polynomials, what is the first term? Again, the 0th term is A0 times B0. Then the first term will be A0 B1 plus A1 B0 times x, and you get the idea, right? So that is called convolution. So this Ax plus Bx is basically just term by term you add for finitely many i's. There are only finitely many terms in a polynomial because you cannot do infinite sum. So this is in f, and this whole thing is in fx. and Ax times Bx is, how do you write this? So you want the coefficient of x to the I, this will be, you have to do Aj Bi minus j. So this is an element in the field, the whole thing is in the polynomial ring. Right, so this is, it's basically, I mean, the sum is a single for loop. You just go term by term, and multiplication is a double for loop, because you want to compute the term for monomial x to the I, but then x to the, so I can be produced in many ways. It can be produced by x to the j times x to the I minus j for various j's. So that's the convolution you have to compute. So this becomes double for loop. The external for loop is for the terms, the internal for loop is for the convolution. So this, okay, and well, so if there are t terms in Ax and Bx, then what is the time needed by this algorithm to calculate the product? T square, right? And for the sum, it's only t, so that's a single scan, that's ordered, I mean, t is the number of steps to compute polynomial sum, and to compute polynomial product, it is t square, so that's quadratic time. Now, in many algorithms, practical algorithms, polynomials can be quite large, so t can be 1000 or 1 million large. So even square seems expensive to certain implementers. So they find faster algorithms to multiply, okay, which is far beyond the scope of this course, but you can learn those things in other courses. So basically sum requires linear time, and the question you can ask is, does product also requires actually quadratic time? So it seems that this is the only definition given, and so it should be quadratic time, because if you have t terms, then there are two for loops, it will take t square time. How can you save on that? But quite counterintuitively, this is not the optimal. So optimal is much faster, because there are much faster algorithms to compute product, which needs too much of algebra. So let me spare you the details. Needs several weeks to explain that. So where are we? We have computed some product, and we have obviously 1 and 0 also. So this fx, right, this is a ring, which is why we call it, we gave the name polynomial ring, because it's, in particular, it's a ring. You can add things, you can multiply things. There is 0, there is 1. There is additive inverse. So the only thing missing is, there is So for example, x will not have a multiplicative inverse. There is no 1 by x. It's not a field. As x inverse doesn't exist. Right, so since x inverse doesn't exist, many other things don't exist, like 1 over 1 minus x also doesn't exist. So any interesting polynomial you take, its inverse will not exist. So this is not a field, but it's a ring, and we'll work with its operations a lot. Um, okay, other properties or definitions here. So for a polynomial AX, so we'll skip AX, we'll just call it A. I mean, when I say A, it will always mean that it's a polynomial in X. In the polynomial ring Fx, we can look at the leading term that it has, or leading monomial. So the leading, okay, let's first write it for A. We can write it as A0, A1x, A dx to the d, where AD is not 0. Right, so as long as A was not 0. So any non-zero element in the polynomial ring obviously has this representation. There is some d such that A0 to AD are the only terms and the last term is actually a term. I mean, we do this because there are also invisible terms, right, like 0 times x to the d plus 1 is also there, and 0 times x to the 2d is also there. Those things are also there, but so actually infinitely many things you can say are there, but they are not playing any role. So we only want to go up to, I mean, especially on computers, we want as small representation as possible. So there is no point storing zero terms. So this is called the leading term. So x to the d is the leading term. We will shorten it to LT, and AD is the leading coefficient. Okay, so a non-zero polynomial has a leading term and a leading coefficient. Only thing missing from this is equal to 0, that we can just say that the leading term is 0. But otherwise there is a non-zero leading term with a non-zero leading coefficient. And this d is called the degree. Okay. So so d is the degree, which we will write as this notation. Okay, degree of A. So degree of 0 we will define to be minus infinity, and degree of anything non-zero will be greater than or equal to 0, right? So if A is in the field, then what is the degree? Degree of field elements is, and yeah, 0. So except 0, f star, then it is 0. And what is the degree of x plus 1? That is 1. And degree of x square minus 1 is 2, and so on. So you get the idea. So degree is basically a map from the polynomial ring to natural numbers. union minus infinity. Okay, so degree sends every polynomial to either 0, 1, 2, dot, dot, or to minus infinity, right? That's the domain and image, domain and range of the degree function, or degree map. And so some important properties of degree that you should remember. What is degree of A times B? If you multiply two polynomials, how does the degree change? Yeah, you can see that it is always the sum. Right, in the case of 0 times b, 0 will give you 0, so minus infinity will go to minus infinity. And if a and b are both non-zero, then you will get a non-zero answer. And you can check from the definition of multiplication that it's the sum, because the leading term times the leading term adds up the degree. What can you say about the sum? Yeah, so for sum there is no such nice formula, but you can check that it's less than equal to degree of A and degree of B. Right, so it's at most the maximum. That's all you can say. Is there an example where it's strictly smaller than both? What is the example? So degree of 1 minus 1, right, that is degree of 0, which is minus infinity, which is strictly less than 0 comma 0. Right, degree of 1 is 0, but then when you add these two things, degree of 1 is 0, degree of minus 1 is 0. When you add these two things, then you get sudden loss in the degree information. Okay, so those proofs you do as an exercise just to understand the definition. You are being given many definitions, so it is natural that most of you will be confused. So you work these proofs out. Okay, one more thing is A is called monic if the leading coefficient of A is 1. So example is x plus 1 is monic, but 2x is not. Okay, so if the leading term is 1, we call it monic. If it's not 1, then we call it non-monic. Any questions? So that is the definition of polynomial ring, and you will be amazed how much we can do with a polynomial ring. Okay, this definition will not go in vain. So most of the remaining course will be just working with this polynomial ring. So yeah, so once you have addition and multiplication, so this is then like, where did we write? So once you have this, that A and B in any two polynomials can be added and multiplied, then you can become greedy, and you may say that, well, like integers, you can add integers, you can multiply integers, and then you can start talking about division and remainder and quotient and GCD and so on. right? Bezout identity, all those things. So all that theory, does it also hold for the polynomial ring? Right? So our goal will be that all those things hold. So polynomials will be the new integers. Okay, that is our goal. So let's prove that polynomials are new integers. So let's define division, GCD, etc. for polynomials. So the major theorem that we want to show is the following. Then everything else will follow, like integers. Yeah, so integers also had prime numbers, right? There were primes also, and then there was also unique factorization. So that also we want to achieve in the polynomial ring. So all these things up to unique factorization we want. So we will start with a statement about division. So for fx and gx in the polynomial ring, for two polynomials f and g, there is a unique quotient remainder pair such that f is equal to quotient times g plus r, where let's assume that degree of f is less than equal to degree of g. I mean, for sanity, you want to divide, so you want to divide by something that is degree lower than the dividend, and degree of r is less than degree of the divisor. Okay, so the degrees are sorted. Degree of f is greater than or equal to degree of g, and degree of g is greater than degree of r. We'll find an r and we'll find a q, and they will be unique. Right? So this you can think of f and g as integers. So whatever we did for integers, we can do here. So what did we do for integers? Yeah, maybe first you have to see this as an example. So how do you divide, let's say, x square plus 1 by x minus 1? Do you remember the division process? Right, so you multiply the divisor by x because you want to cancel x square, and then you proceed. So what that process gives you is it will write x square plus 1 as x minus 1 times what? And what will be the remainder? So remainder is 2, and you get here x plus 1. Right, and that's the divisor. So this is again the long division process that you have learnt in school. So using that you can get quotient and remainder. In those days you didn't know, you were not aware what you were doing, but now we will show that all you need is field property. Okay, as long as you are working over a field, that whole long division process works. And yeah, if it's not a field, then there will be problems. But for a field, there is no change in the long division algorithm. Yeah, so with this example, now the proof can be formalized. What we will do is we will do this by induction. So you compare the leading term of f with the leading term of g, and you kill the leading term of f basically. So f becomes smaller. Then you continue long division for a smaller instance. So base case is basically the example I wrote. So proof will be by induction. induction. So this is the base case. I mean, or you can take a even smaller base case. You can just take f to be constant, g to be constant. Then what will happen if f is 1, g is 1, then what happens? That's the smallest base case, right? So 1 is equal to 1 times 1 plus 0. Then r will be 0, so degree will be minus infinity. It will be even smaller, much smaller than 0. So those are the base cases. These you can clearly take care of. And use induction on the degree of f. Okay, so we'll reduce the degree of f in each step. So what is the induction step? Let's see that. So let's write that expansion. So f is fn xn and g is gm g0 and m is less than equal to n. Right, so those are the field elements, fi's and gi's, other and then you have the x monomials. So long division, the first step is you just cancel x to the n, right? So target xn, that's the first step, using x to the m. Long division doesn't really, the first step doesn't really care about what the other fi gi's are. It only looks at the leading things and compare and divide. And what does it do? So it basically does that. It will do f minus so in G you multiply, what should you multiply? Important thing to remember is that this guy is non-zero, right? Gm is non-zero, Fn is also non-zero, but that's not very important. What's important is by what you are dividing, so that is Gm. So you can multiply G by Fn Gm inverse times the x part, which is n minus m. Right, so basically scale up G. So if you scale up G enough, then it will become Fn xn. Then you can cancel. And what you will be left with is that's complicated to write. So it's Fn minus 1 minus, so let me call this something, let me call this Q or U. So gm minus 1 x u times u, it's not a good choice. So what I should do is f minus g times u times x to the n minus m. The constant thing I call u, and then I can write in terms of u. So it will be this times u times, what is the x part? N minus 1. Yeah, and that's the pattern. And it goes till where? So we are multiplying only g, right? So it will go up to g0 x n minus m. So what is the f part that comes with x to the n minus m? F n minus m. Plus, so the remaining part is unchanged in f. So that is f n minus m minus 1 to f0. Is that clear? That's basically the whole long division algorithm. Right? If you actually code this as a C program, this is what you will do. Those are your variables, and you will subtract from f a proper multiple of g, which is given by u times x to the n minus m, and which when you take the difference, multiply and take the difference, you will see that you get coefficients of, early coefficients of f, they will all be changed, and later coefficients of f, they will not be changed. Right? It works for any mn. Okay, so the thing you should look at is that this is a smaller instance, because now the leading term of this difference is not x to the n but x to the n minus 1, and you repeat this with g. So this is the induction step, and since its degree is less than n, which was the degree of f, we can use induction hypothesis, or basically in the algorithm it will be a recursive call. Well, so what will induction hypothesis give you? What was G supposed to do? It was supposed to keep dividing all these long division steps, and in the end give you a remainder whose property will be what? Should be less than the degree of G, right? So we can use the induction hypothesis to get a remainder R with degree less than degree of g, which was set to be m. Right, so the degree of on the f side it keeps on decreasing, and then the process or the recursive calls will, in the base case, they will halt when it's smaller than the degree of g, because then g cannot help. Right, this induction step assumes that g has lesser degree, less than equal to f. So below degree of g, the process halts. So you get an R, and what is the quotient? How does the quotient evolve? So at this point, quotient is basically the way it is evolving is this u that you got, right? This thing, this gets in every step it adds. So you will get a quotient whose degree is what? It's n minus 1, because the maximum one I have shown you, the other ones are less than n minus m. This gives quotient q, which is this fn by gm, or same notation. Which is the degree of f minus the degree of g. Okay, so that's the whole algorithm, and it's a constructive proof, gives you an algorithm. So you get q and r. So we can add that here. Okay, so degree of q is degree of f minus degree of g, and it's exactly that, and the degree of r is something that is strictly smaller than degree of g. That's the property of division. Final thing is, why is it unique? Well, this implies that we have written f as q times g plus r. And let's handle the uniqueness now. What's the proof for uniqueness? Suppose not. So then you have f equal to q1g plus r1, q2g plus r2. Then what? With the property that r1 and r2 both are degree less than degree of g, right? Then what happens? No, you subtract. So q1 minus q2 g is equal to r2 minus r1. Right, you take the difference of the second and third polynomials, you rearrange, you get this, then what? Compare the degrees. So this is degree less than degree of g, and this is, this whole thing is degree greater than equal to degree of g. right? So that is a contradiction unless so it implies what? Yeah, actually we assume that R2 in R1 is not 0, so let's continue with the contradiction. So we had assumed that this is not equal to 0. R1 is different from R2. In that case, this has led to a contradiction. You don't have to say anything. The contradiction implies that it's unique. So R1, R2 equal means that Q1, Q2 are also equal. Is that clear? Yeah, so this is a fundamental thing. The way you learn division in school, it's actually a method that holds for any field. Over any field, polynomials, you can do the same. Can you go back and compare this division theorem with integers? Or even the algorithm, the long division algorithm? Is it the same algorithm as you do for integers? Why is it the same? What is x in that case? Yeah, so for numbers, x is 10. So x equal to 10 recovers the integer division algo. Right, so this is the reason why these polynomials, these are the new integers. Okay, so to you polynomials, I mean, we'll prove so many properties for polynomials that they will become, they will look no different from integers. Okay, they will behave very much like integers, but the advantage is that proving properties of polynomials will somehow be easier than proving properties for integers. So this is why algebra is considered easier than number theory. Okay, we'll slowly see examples of that. Okay, so what can you do if you can do division? So using the division algorithm, well, let's first define the GCD business. So for polynomials f and g, the greatest common divisor GCD of f comma g, where we'll usually write like integers f comma g, we'll shorten it to f comma g. So the GCD of two polynomials is, it has to be somehow greatest and it has to divide, right? So greatest, it will be in terms of degree. So now we cannot talk about biggest integer, we have to talk about somehow biggest in the polynomial ring. So biggest in the polynomial ring is by degree, degree is the measure. So we say that GCD is the largest degree H such that H divides F and H divides G. We should also say that it's monic, so largest degree monic polynomial. Okay, So that is the greatest common divisor of two polynomials. Example, what is the GCD of 1 and x? Right, that will be 1. What is the GCD of x? X square plus 2x, that is x. Let's say GCD of x plus 1 and x cube plus 1. X plus 1, right? So I did not say the field, but this is, let's say, happening in rationals. Let's check it. 2x and 4x. Yeah, what do you want to say? What is the GCD? GCD is x. That is why I added monic, so that there is no confusion. Because some people here think that the GCD is x, some think that it's 2x, some think that it's 100x. All the answers are correct, actually. The reason is that 100 divides 2 and 100 divides 4 also, right? That's the new rules in integers we are following. Polynomials are the new integers. So now in the ring of polynomials, 100 does divide 2, right? 3 divides 2. Why is that? Because because 3 can be written as 2 times 3 by 2, and 3 by 2 is an element in the field. In fact, it's an element in the polynomial ring, sorry. So 3 divides 2 because there is a polynomial which multiplied by 2 will give you 3, and that polynomial is 3 by 2, right? So there are actually infinitely many GCDs if I am not careful. It's a weirder arithmetic that we are not doing. But if you say monic, then everything is fine, because monic there is only x. I mean, again, these things I am saying, you prove this formally, because I am sure you haven't understood the definitions well. So you do the examples formally and then you will understand.